In this video, we are going to take a closer look at the mathematics behind this vapor pressure temperature relationship that we explored in the previous video using the so-called Clausius-Clapeyron equation, named after the two scientists responsible for a lot of the initial work in this regard. So to start things off, I want to recall from the previous slide that, or previous video rather, that basically when we're looking at vapor pressure of a liquid, right, this is a sort of a measure of the tendency of these molecules to escape that liquid phase and move into the gas phase. We find that this vapor pressure increases with increasing temperature. Okay, and of course this was not surprising given the fact that increased temperature gives rise to increased kinetic energy or average kinetic energy of the molecules in that liquid, and as a result a higher probability that a given molecule at the surface of that liquid will be able to escape, break the bonds, holding it to the liquid, and enter into that gas phase. Okay, so it's not surprising at all then that the pressure increases with temperature. What is perhaps more surprising is the actual shape of these vapor pressure curves. So notice that in every one of these examples, there's this sort of curved appearance to these lines. And what we're going to do here in this lecture is explore the mathematical description of this curve, and we're going to find that in doing so we can actually pull out a lot of very interesting properties of the substance itself. In particular, we're going to be able to find that by looking at this curve closely, we can get an idea of the energetics associated with this vaporization process. Okay, so if you look closely at the shape of this function and you play around, maybe with your plotting tools, you can perhaps convince yourself that this curve is in fact following an exponential form. And the vapor pressure then, we're going to denote as P vapor, is related to the temperature as follows. Vapor pressure is equal to some constant, A, times E to the power negative delta H vaporization divided by RT, where R is our good old friend, the gas constant, and delta H is that enthalpy of vaporization, which again, I want to remind you, enthalpy of vaporization is the energy that must be supplied as heat at constant pressure to turn a liquid into a gas. In other words, it's a measure of how much energy is required to break those bonds holding that liquid together. Okay, so you can see right off the bat now, if we have this plot, this exponential plot here, we can somehow then back out the value of this enthalpy of vaporization. Or in other words, we can understand how much energy is required to break apart those molecules. All we need to do is be able to come up with the function that represents this curve. All right, so of course, there's a problem right off the bat. In practice, what you're really going to have is not a smooth curve from your data, but what you're really going to see is a set of scattered data points. Okay, maybe you'll come up with a set of data points like this, right? And it's a rather hard problem to work with a set of data points and try and fit an exponential to it. Now, certainly it's something we can do, but in general, and for a variety of technical reasons, it's something that we try to avoid if at all possible. Okay, so working with the Clausius-Clapeyron equation as it's written here in exponential form is hard. So what we're going to end up doing is basically remove that exponential piece, right? And we're going to do that by taking the natural logarithm of both sides of the equation. So we know from our property of logarithms, we can take the natural log of p, get that on the left-hand side, take the natural log of this product, it turns into the sum of the natural logs. Natural log of e to a power, we just return whatever's in that power term here. So you can pause the video here, make sure that I'm not doing any sleight of hand there with the algebra. It's all, again, basic manipulations of logarithms. Okay, now what we're going to do next is take this equation that still looks a little unwieldy and rearrange it to get it into a much more familiar form. So notice that if I take this ln of P vaporization, keep it on the left-hand side, then basically just swap the order of the two terms here on the right-hand side and pull out a 1 over t, we're left with a function that has a very familiar form. It's the equation of a line, where the y value is our natural log of P vaporization, and we now have a slope and an intercept well defined. The slope here in green is going to be negative, that change in enthalpy of vaporization, and divided by r, of course, and the intercept is the natural log of this constant a. Okay, so what this allows us to do then is, rather than plot P as a function of temperature, we can plot natural log of P as a function of 1 over the temperature. And if we do that, as you will no doubt be not surprised to see, all right, we get roughly a linear relationship between these data points. And so looking at a set of, again, actual experimental data, and in black points here, we see a bunch of points that almost lie directly on a single line here, okay? And once you have points on a line and you want to fit a line to a set of data points, this is a relatively straightforward problem that can be done. Standard least squares techniques work. Any of your modern, calculators, or you can do it on Excel. Many different applications allow you to carry out this line of best fit procedure. Okay, and so this gives us now a way to collect a set of measurements, a set of temperature and pressure measurements, plot them, specifically plot the natural log of the pressure and 1 over the temperature, right? And then look at the characteristics of that line to draw out information from the slope that will tell us basically the energetics associated with that vaporization process, right? Okay, so but really there's kind of two approaches here, right? The approach we saw on the previous slide is an approach that you would take if you had multiple data points, right? So this is the so-called line of best fit method for determining the enthalpy of vaporization using the Clausius-Clapeyron equation. So basically, you take a set of measured values, the pressure, vapor pressure, and temperature, make that plot of ln P over 1 over T, find your slope of the line of best fit. You know that slope is equal to minus delta H over R. You then solve for delta H, and you're done. Okay, now, this is obviously not the only way to do it. You can get a line of best fit by only having 2 data points, right? So in a very simple application of the Clausius-Clapeyron equation, you could have only 2 measured values, and this gives rise to the so-called 2-point method. If you have only 2 measured values of temperature and pressure, you can plug just those 2 values into the Clausius-Clapeyron equation to get the so-called 2-point form of the equation, boxed here at the bottom, right? Then, because you know P1, P2, T1, T2, you can plug in those values and solve for the enthalpy of vaporization. Okay, so of course the 2-point method is ostensibly less work, right? I mean, you just have to plug in 2 data points rather than a whole set of them. You don't have to do linear fitting models and all that sort of stuff, right? So then the question we want to consider is, well, why would you ever do more, right? Why would you do more work than simply using the 2-point model? Well, really the key take-home message comes down to, the accuracy that you're looking for in your predicted enthalpy of vaporization. Remember, data is not perfect. There's always errors present. So the more data points you use, the more robust your line of best fit and the more accurate your enthalpies of vaporization, right? If you only use 2 points, then you run the risk of basically skewing your data, and perhaps skewing your data quite significantly. So the figure on the board here illustrates a couple different cases where you could say use the P1 and P2 circled right here make a line of best fit, and you see that that blue line actually deviates rather significantly from the red. And if we just randomly pick another 2 points here, P1 and P2, we get yet another line that deviates from that red line, our line of best fit. So in other words, using the 2-point method gives you a much higher chance of error. Of course, you could get lucky, but chances are you're going to be introducing more error and perhaps significantly more error. So in an actual experimental setting, you'd actually want to be using that linear fit model. However, in the context of solving some basic problems, we can do a pretty good job using the 2-point form. Okay, so to see how to do this, let's consider a final example here using the 2-point form of the Clausius-Clapeyron equation to make a simple prediction. Okay, so in this example, we're told that we have a methanol, and it has a normal boiling point of about 64 degrees Celsius and a heat of vaporization of 35.2 kilojoules per mole. All right, now our job here is to determine what the vapor pressure is of methanol at 12 degrees Celsius. Okay, so the first thing to do here in this problem is to remember that there's actually more information that we're given than perhaps first meets the eye, right? Remember, we're told that the normal boiling point is this 64.6 degrees Celsius. What does that mean? Well, remember, the normal boiling point is the temperature at which the vapor pressure, matches that external pressure, 1 atm, or 765 millimeters of mercury. Right? In other words, we have a point already, right? But one of our 2 points that we'll use in the Clausius-Clapeyron equation, namely, the pressure 1 is 760 millimeters mercury, and the corresponding temperature is then going to be 64.6. Okay, and then our problem then boils down to saying, okay, well, that the second temperature, right, we're given 12 degrees Celsius, we want to then determine what that pressure P2 will be. All right, so we're going to use the 2-point form of the Clausius-Clapeyron equation and solve for this unknown P2 value. Okay, so plug in everything. We know the R, of course, is the gas constant. We're actually given the enthalpy of vaporization here. We can plug that guy in too. All that we really have to do here is do a little bit of algebra to solve for P2. So to solve for P2, the approach that you're going to take is, take the exponential of both sides, right? So raise both sides to the E, right? And so if we do that, then that, of course, gets rid of the natural log on the left. We can multiply P1 up on the right. This entire term up here will then show up in our exponential. We can plug in all of the known values on the right-hand side, and we will arrive at the value of 75.4 millimeters of mercury. Now, I encourage you guys to work through that algebra on your own, plug that in the calculator, make sure that you're comfortable with solving a basic problem like this, right? And so you can expect that there are a variety of different ways this problem can be asked, but it all boils down to, you're going to be either, you've got really 5 variables here, the P1, P2, T1, T2, and the enthalpy of vaporization. The problem will give you some subset of 4 of those and ask you to solve for the 5th. Okay. Now, the final thing I want to point out here, when you're looking at enthalpies of vaporization, these are going to be positive values, right? Because it's the amount of energy that must be put in to break apart the intermolecular interactions in that liquid. Okay, so they are positive values. And in fact, the fact that enthalpy of vaporization is positive and energy is required to break bonds is really the foundation of why sweating keeps us cool. Okay, so to understand that, remember this fact: you're breaking apart bonds, right? Energy has to go in. This is an endothermic process. Okay, so conversely, if you have a condensation process occurring where you have gas going back down the liquid, right, then energy is going to be released. So what happens if you sweat? Well, when you sweat, you basically are putting a bunch of liquid molecules on the surface of your skin. what's going to happen then as these molecules on the surface of your skin break apart and go out into the gas phase, right? We are breaking bonds. We are breaking intermolecular interactions. That energy has to come from somewhere. Well, that energy comes from your body, in part. Of course, it also comes from the surrounding environment, but your body's a big part of that surrounding environment, especially if that sweat is sitting directly on your skin. So that evaporation process is actually taking energy out of your body, putting it into these gas phase molecules that then spin out into the surrounding environment. Okay, so that wraps up our discussion of the Clausius-Clapeyron equation. I encourage you guys at this point to, hop on Canvas there, work through a number of other example problems to really make sure you're comfortable using that two-point form of that Clausius-Clapeyron equation.